All right, so as Tanya mentioned, my name is Ritika Chaturvedi. I am a biomedical engineer at the Schaefer Center, also at USC. We sit right next to Caesar, loosely affiliated. So I am going to talk about using Fitbit data from the American Life in Real-Time study, which is the study that I lead in partnership with the UAS. So giving you a little bit of a rationale as to why we set up this project. So this project is really built to enable more equitable digital health. So what is digital health? Digital health is really using digital technology, smartphones, wearable devices, Internet of Things to improve health and well-being of populations. And the way that this works is that these devices produce constant data, which are called person-generated health data. So this is everything from your wearable signal on your Fitbit or your Apple Watch to your smartphone, keystroke patterns, and what have you. All of these data get produced by individuals, they get fed into algorithms, and these algorithms then iteratively improve health over time. So for example, if we see that you're not getting enough sleep, we might recommend that you get, a few extra minutes of sleep every night, and that algorithm then measures whether or not you have actually followed through in that recommendation, and then kind of tweaks that recommendation at the individual level over time. Now, this is a very, very promising field. AI and machine learning are kind of exploding all over the world. But what is happening is almost all of this work is being done in the industry, and industry cares about users using their platforms. Industry doesn't necessarily care about non-users. And this is where the UAS comes in. So I really wanted to enable a digital health study that studied population health using these technologies that actually looked at both users and non-users, because as you can imagine, non-users are not very representative of the population. So kind of the way that this was set up is we have a probability sample of individuals. We started with the UAS. We sampled about 1,000 people of them, oversampling for underrepresented individuals, historically underrepresented individuals. And we created an infrastructure that allows us to overlay digital technology signals on a time series for each individual. So currently we have surveys through the UAS. We have the Fitbit devices that we provided to 1,000 people. And then we have the public data sets. But this infrastructure is also flexible to accommodate other wearable signals, other digital technologies. As long as it has an API that we can access, we can integrate it into this infrastructure. So currently we have, Fitbits, but the sky's the limit. We could add electronic health records, we could add genomics, other medical devices such as continuous glucose monitors and what have you. All of this data gets fed onto individual level time series, and then this enables, digital health modeling and interventions based on, traditional statistical approaches as well as machine learning and artificial intelligence. So in order to do this, we created a custom smartphone app. This app, because we're dealing with a population that might not be digitally savvy, the app actually walks people through all of the connection steps, downloading each of the various apps. So for example, for Fitbit, you have to also download the Fitbit app and pair the two together so that our study app talks to the Fitbit app. So the app actually in its setup process does it in a very, very easy way so that the participants don't have to click on a lot of different icons on their phone, so that the app does most of the work for them. Once they have enrolled in the app also facilitates surveys. It allows the participant to view their Fitbit data. And it also keeps track of their study activity through engagement science. So essentially, we incentivize completion of each study activity with a certain number of points. And at the end of every month, those points get redeemed for monetary value. And what we mean by activities is not only points for surveys, we're giving people points for actually wearing their Fitbit every day, because we really want to get them into the habit of just wearing the device and keeping it on them. So based on this, the Fitbit data that comes in, it comes into on a monthly basis. And It's in two different categories. So we have the calculated metrics that Fitbit derives. So these, if anybody has a Fitbit, you have, your step counts and your sleep scores and things like that. So those are the metrics that Fitbit calculates, but we don't actually know how they calculate these metrics. They're just there for us to use. And these are at the daily level. And currently we have steps, sleep, activity, and heart rate. But in the future, we're also going to get temperature, oxygen, and a couple other variables that Fitbit is currently in the process of testing, as well as, future variables that are coming down the pipeline, like Apple's glucose monitor or Fitbit's blood pressure sensor. But really, where the power of these data come in are on the other side of the data, where we get minute level data for each of these sensors through the Fitbit API. So steps, we get minute level data for counts and distance. For sleep, we get minute level data for duration, efficiency, sleep onset, offset, latency. But what this means is because these are on minute level time series, you can derive additional measures or features. So for example, for steps, distance over time is walking speed. If you have any irregularity in how your distance over time gets calculated, then that is, differences in gait. For sleep, you can do circadian rhythm, you can do chronotypes, you can do sleep staging in combination with heart rate and things like that. So as we get more of these metrics on a time series, we can start to see how powerful these become specifically for machine learning and AI purposes. So just to give you a couple examples of how this might work in practice, on the left, we have essentially the day in the life of the 1,000 people in the panel, where the blue line represents people who have diabetes, and the red line represents people who don't have diabetes. And this is essentially heart rate, which is beats per minute, plotted over a day, averaged over all of the days that we have data for individuals, and then averaged over the population. So you can see that there are clear differences in, for example, so first of all, the heart rate makes this nice sine wave, right? You have, at t equals 0, which is midnight, your heart rate kind of declines. It reaches a trough, which is essentially your resting heart rate. And then it starts to go up as you wake up. And then there's a lot of variability over the days as you are active and so on and so forth. And then as you wind down for the night, it starts to come down. So if you just plot this over days, you just see a nice sine wave moving on through people. But now if you average it across different populations, you can start to see how there's heterogeneity in these signals. And these heterogeneities actually matter when developing these algorithms. On the right, you can see even within diabetes, if you look at what this curve does across races, you see that there are differences even within diabetes across races. And this is how you start to understand, there are disparities in how, African Americans or Latino people experience the disease versus, non-African American or Latinos, right? And you can see how these sorts of differences may explain some of the disparities in these disease states. So another example I have is COVID. Now, hang on, this is a little bit of a complicated graph, so I'm going to try to explain to you what's happening. So on the left, you have, on the top left, you have resting heart rate. On the bottom left, you have activity. On the top right, you have sleep duration. And on the bottom right, you have sleep efficiency. Now, what we're looking at here is deviations from individual specific baselines. So prior to the COVID infection, right? So we're essentially taking each day minus a baseline. So prior to the COVID infection, you would expect that, the signal is around 0, which you can see for COVID negative blue and COVID positive, it's about the same. But starting around, a couple days before their self-reported infection date, you can start to see that there's something going on, where you see a significant rise in heart rate. You see a significant decline in activity. You see a significant rise in sleep duration and a significant decline in the quality of sleep. So even though you're getting more sleep, the quality is actually not very good. So this is interesting for a lot of different reasons. So first of all, just for characterization, right? So we know that there is some sort of signal in the Fitbit data that's predicting that some sort of infection is happening. Not only that, you can see that after the acute infection period, you still see significant variability in these signals in the post-acute period, which is indicative of long COVID or post-acute COVID syndrome. And actually, in some people, we see that this fluctuation goes past 60 days. So there's definitely something going on there as well. But just from a methodological perspective, first of all, we observed 130 COVID positive cases over 1,038 participants versus in digital health studies that use primarily Fitbits and Apple Watches from self-selected owners, they look at 20,000 participants and they can barely get about 200 people in sample size. So it really shows how selected the digital health studies are in this space. The second interesting thing is about if you run an algorithm, so there are many algorithms that already exist that look at predicting influenza-like illness based on wearable signals. If you run those algorithms on our signal, we find that 80% of COVID positive cases, the signal starts within 3 days of their self-reported date. So that's a really interesting way to actually verify that, self-reports are actually pretty accurate, especially in this case when they're trying to recall a COVID infection date. So from a methodological perspective, it's interesting to have that kind of verification. And then finally, what's interesting in here is we can also develop predictive algorithms with actually pretty good sensitivity and specificity. So not only does this, from a health perspective, this lets us develop, potentially messaging strategies. Oh, we think that you might have COVID. Maybe you should test, or maybe you should stay home from work today. And we could test the efficacy of those interventions. Alternatively, we could also just develop passive predictive algorithms that just run in the background of our collection. And all of a sudden, this becomes a surveillance tool. Especially in a large population, we can see if there's geographic areas that we're seeing spikes in these signals. All of a sudden, we can track flu, we can track COVID, we can track future pandemics to see if there's any local, endemic outbreaks. So I just wanted to leave, the way that the study was designed was meant to be a very holistic way to study health. It's meant to pair with any of the UAS survey data to see if there's any sort of features that correlate with the Fitbit data in order to develop these predictive algorithms. So this is just, one case using COVID, but, the sky is kind of the limit here. So yeah, and Tanya did show this picture before, but this is one of our favorite pictures. This is Eva, who during the pandemic single-handedly mailed out 1,038 Fitbits to enable this project. And then the last thing I'll say is that this is an effort that we are going to be continuing and looking to grow. So not only are we trying to grow alongside UAS's growth, but we're also trying to keep these people engaged over long periods of time. Currently, we have about a full year of data on 1,000 participants. Those participants, many of them are choosing to continue past the year. We're also recruiting new participants into the sample. So hopefully the sample size grows over time, and the sheer amount of data will also scale up. The data are not quite available yet. They will be available sometime this summer. So they're coming, but just be a little patient. And that's all I have.